So we're looking at geometric representations of our x squared and x cubed. So this is kind of the meat of the unit introduction to get the concepts down. We've kind of done this a little bit before, especially with the area concept, but we're going to formalize it a little bit more here. So some definitions. Variable, which we've worked with in the past. It's defined either as an unknown quantity or a quantity whose value can change. And if you take a look at our example, in example A, as an unknown quantity, 3 plus x equals 7. So there's some number that x can be. We don't know what it is. We can now solve for that. Yes, you can figure out it's 4, but we didn't know that until you actually figured it out. What do you add to 3 to get 7? 9 divided by x equals 5. What's x? Well, 9 divided by something is 5. And we can figure out that is 1.8. So it's an unknown quantity that we're representing with the variable. And then in example B, the quantity whose value can change. And here you see in the area equals length times width, the variables don't have to be x. They can be other number or other letters. So we have area equals x times or L times W, length times width. And so this is where we see the values can change. The area changes with the length and width. If the length is 5 and the width is 6, the area is 30. So A becomes 30. But if the length is 7 and the width is 8, then the area becomes 56. So there is a variable changing quantity. Y equals 4x plus 1. This is a partial variation starting with an initial value of 1 and then a rate of change of 4. But as we change x, if we were to make a table of values, we'd select a few different x's, and then we would get different y's. So x and y are quantities whose values can change. Technically, we do not have to use the letters. You could use anything. You can use happy faces. You could use a little picture of a unicorn. We could actually write, I don't know, happy face equals 4 times unicorn. That's my unicorn drawing. Don't make fun of my terrible drawing skills. Plus 1. This and this are the same. It's just a symbol. We use letters because we're familiar with letters and they're easy to work with. Drawing unicorns every time might be difficult. So the next definition, an algebraic expression, and this is different than an algebraic equation, which is another term we'll use in later sections. An algebraic expression is a math statement with numbers and variables connected with mathematical operations. No equal signs, though. So 3x minus 6, 4 plus 7y, those are algebraic expressions. Now, those algebraic expressions are made up of terms. And a term is a number, variable, or a combination of the two that is separated by a plus and minus sign. So some examples of one-term expressions are x, just the variable, 3, just a number, 7x, a number and a variable, but it's not separated by a plus or minus, so it's only one term. 4x squared plus y, again, no plus and minuses, so it's only one term. Two terms, we got x plus 3, 4x minus 8y, 6 minus 4x. These are two terms because we have a plus or minus separating two separate individual terms. Three terms, x squared plus 6x minus 2, 7ab plus 4a minus b. These are separate terms with plus and minus signs in between. Now, getting to the concept of the geometric representations, when we have something like a length model, so we're going to do length, we're going to do area, and we're going to do volume models. When you see a variable with no exponent, you can treat it as if it was the length of an unknown value. So if you see x, you should picture a line. Doesn't matter the length of the line as long because you don't know the length of the line. Just x represents the length of a line. We don't know it. When you see 2x, well, that's two lines of the same length that we don't know. So there's our picture. 3x, you should picture 3 lines of some unknown length. And so this is a good way to visualize what these represent, and this is going to help when we're comparing them to x squareds and when we're comparing them to x cubes, because this is one of the things that will later, when we get to that, collecting this idea of collecting these different terms, students get confused by. So when you see x, just the letter x, no exponent, or A, or B, or unicorn, or happy face, you should picture it as the representation of just a line. So an example here, working with this, we're going to make a model, mathematical model using this. In the SC or FSC race series, this is a super fast car race series. Cars complete 12 laps every race. The tracks for these races have different lengths, however. So we want to create a mathematical model to determine the total distance the cars travel in a race. So every race they're going 12 laps, but we don't know how far they're going. So that's our unknown value, is how far they're going. So we'll call that the D for the distance, or let's call it L for the lap. Call it L for the lap. So the distance traveled, we use D for distance, equals 12, and then that's times the length of a lap. So 12L. And again, I use the cursive L just because I don't want it to look like 121. So the distance equals 12 times the number of laps. That's it. We've now made a mathematical model to use on any of these races. So if a track says our track length is 30, it's 12 times 30, which is going to give us 360. 30, maybe it's 30 kilometers, it's 360 kilometers in total that the car has to race that time. If they say, another track says, well, our track length is 200 kilometers, well, that's 12 times 200, which is going to be 240 kilometers the car races. So we can use that as a mathematical model, possibly graph, and then we can graph that along the way as well, things like that. So this would be an example of a direct variation. Now, moving up in dimension, we're going to area models. When you see something raised to the exponent 2, for example, 4 to the power of 2, we call it squared. We say it's 4 squared. The reason why we use this term is that you should be visualizing the square of that area, and we talked about this concept before when we were working with area. So when you see something squared, x squared, what you should picture is a square of unknown size, of unknown dimensions. Just x by x. But when you see x squared, you should picture a square. So when we see x, we picture a line. When we see x squared, we picture a square. So 2x squared, you should see 2 squares. 3x squares, well, that should picture 3 squares. So let's make a model with this. A neighborhood association restricts the dimensions of front gardens to equal length and width. And I'll tell you, these neighborhood associations sometimes are a little crazy. This one a little excessive maybe. But they have rules that you have to do this. You have to water. You have to keep your lawn watered. You can't have dandelions, or you can only have, your house has to be so far from the curb. You can't have pink fences. Whatever, they make rules. So this one's a little crazy and has a rule where you can only have front gardens that have equal length and width. Equal length and width means we're going to have a square. So we're going to have a square shape here. And so if we have this square shape, doesn't tell us how big they need to be in length and width, so our dimensions are x by x. Well, the area of these gardens could just be represented by x squared, or L squared, or W squared if we want to use length or width for that, but their length and width are the same, and so we're modeling that with x squared. And then we can jump up to the third dimension and look at volume models. So we use the term cubed when discussing values raised to the power of 3. This is because you should be visualizing a cube with a side length of that number cubed. So when you see x cubed, you should picture a cube with side length x by x by x, or dimensions x by x by x. When you see 2 cubed, you should picture 2 cubes. When you see 3 cubes, you should picture 3 cubes. So that's what we're doing here. So now we have a situation here to work with. So there's a company called Cubots, and it sells mini connectable cubed-shaped robots. And these are actually, I've seen things like these. These are actually pretty cool, and they can do some cool stuff. They can connect together, and then each robot can become an arm or a leg or whatever it needs to be in the case of the robot. Anyways, Cubots sells their cube-shaped robots in sets of 3. And so a designer is hired to make an efficient package design while he's waiting to get the actual product dimensions. They said, we need you to make packaging for our cube-shaped robots. He's like, okay, that's cool. So what are the dimensions? He doesn't know yet. And so he's waiting for those to get back. But he said, I'll start doing designs on the computer, and then I can just scale it to whatever dimensions I need to later. So he's going to design this with a square-based prism as our shape, and we want to create a mathematical model for this volume. So we're going to have this square-based prism, and there's going to be 3 of these cubots in here, and they're all squares. So we don't know the dimensions, so the square part is x by x, and then this is x, but there's 1, 2, and 3 of them. So this here, 3 cubes, that's 3x. Right? There's a length of x, a length of x, a length of x. That's 3x. Like we talked about in the linear part. So we got 3x, and then we got x by x here. So the volume is 3x times x times x. And knowing what we know about exponents, when we multiply x by itself 3 times, what we're going to get is x to the power of 3. And there is our volume model. So he can use that as the volume model for this packaging. And then once he gets the actual dimensions, he can set the x value to whatever it needs to be in this case. So again, when you're working with these, we have our variables. When you see x or just a plain variable by itself, y, unicorn, picture a line of length unicorn. When you get x squared, picture a square with dimensions x by x, unknown dimensions. So 3x squared would be 3 squares of unknown dimensions. In the case of our volume here, we got 3x cubed. And if you look at it, here's 1 cube, x by x by x, x cubed. 1, 2, 3 of them. There's 3x cubes. And that's what we're picturing there. And again, we don't have to use x's and that. We can use other letters as variables, or we can use symbols, whatever we want. Letters, though, being the most easiest. So that is our introduction to our algebraic unit.